two numbers are tearing cosmology in half. 73 versus 67. That doesn't sound like much until you realize those are supposed to be measurements of the same thing, in the same universe, with instruments and statistics that claim they're precise enough to be done arguing, and they aren't. If the universe were a clock, this is the moment the hands disagree about what time it is, by enough that you can't pretend it's a rounding error. So the question isn't who's wrong, the question is, what kind of measurement produced that number? And what did it assume to get there? Because here's the secret. 73 versus 67 isn't one debate. It's a family tree of methods, each with a different hidden lever that can quietly push H0 up or down. And if you keep thinking Planck versus SH0ES, you're going to keep getting confused every time a new paper drops. Physicists Ioannis Pantos and Pantos Perivolaropoulos released a synthesis in January 2026 that basically says, we're framing this wrong. They grouped dozens of modern Hubble constant measurements into method families, based on what each method assumes and what it tries to avoid. And their conclusion lands like a diagnosis. This isn't early universe versus late universe. It's closer to distance ladder versus most other methodologies. So in this video, we're building a method map you can actually use. And I'm giving you a filter, a three-part question you'll ask every time you see a headline about H0. Which family? Which knob? Is it independent? Say it once because this is your superpower. Which family? Which knob? Is it independent? Now, start with the simplest definition of H0. H0 is the present-day expansion rate of the universe. In practice, every method is the same skeleton. You need a distance, you need a redshift. You turn those into a slope. That's it. All the drama comes from how you get distance and what assumptions sneak in while you do it. So here's the map. Not two families, 4. And each family has a different hidden knob, a place where assumptions can quietly push H0 up or down. And once you see those knobs, you realize something unsettling. There are only a few places a 9% shift can hide, and every method is betting on a different one. Family 1, the distance ladder. Family 2, local one-step measurements that assume ΛCDM, the standard cosmological model. And family 3, pure local. One-step measurements that try to avoid assuming the detailed shape of the expansion history. Family 4, CMB sound horizon-free measurements, using CMB information, but deliberately not locking in the usual early universe ruler. If that sounds like alphabet soup, good. Because the point isn't the labels, the point is the knobs. Distance ladder's knob, calibration and astrophysics. Local one-step with ΛCDM's knob, the assumed expansion history. Pure local one-step's knob, method modeling, with minimized cosmological priors. CMB sound horizon freeze knob, which early universe constraints dominate when you refuse to lock in the standard ruler. Now, we're going to build these families one by one. And as we do, keep using the refrain. Which family? Which knob? Is it independent? Because that's the whole game. It's family 1, the distance ladder. The distance ladder is the classic approach. Build distance outward rung by rung. You start with geometric distances close to home, parallax in the Milky Way, and other geometric anchors for nearby galaxies. Those anchors calibrate standard candles like Cepheid variable stars. Cepheids then calibrate type 1a supernovae in galaxies where you can observe both. and Type 1a supernovae are bright enough to carry the scale far into the smooth Hubble flow, far enough that local gravitational motions don't dominate. This is where 73 usually comes from. According to a comprehensive SH0ES collaboration analysis led by Adam Rees, released as a full measurement write-up in late 2021, the team reports a Hubble constant around 73 kilometers per second per megaparsec, with uncertainty around the 1% level. But that's the 73 side. Now here's your first cliff turn. If the ladder is that precise, how can it still be wrong? Because the ladder's precision depends on calibration, on how perfectly you set every rung. And calibration is the ladder's hidden knob. A few percent shift in one rung is exactly big enough to move H0 by several kilometers per second per megaparsec. So, the distance ladder isn't one method. It's a bundle of choices. Which geometric anchors do you trust? How do you correct for dust? How do you handle crowding, stars blending together in distant galaxies? How do you treat metallicity effects in Cepheids? Which supernova sample do you accept? How do you standardize supernova brightness without introducing selection bias? This is why the James Webb Space Telescope matters here. Not because Webb magically solves the tension, but because it changes the systematics inside the ladder. In 2024, astronomer Wendy Friedman and collaborators released a JWST-based status report from the Chicago Carnegie Hubble program. They compared multiple stellar distance indicators, ways to replace or cross-check Cepheids, and carried those calibrations into supernova hosts. And the revealing part wasn't one number. It was that different indicators cluster differently. Some landed in the high 60s to about 70. Cepheid-based calibrations remained higher. Their combined value landed around 70. That's not a solution, that's a clue. Because it says the local distance scale is sensitive enough that a few percent shift, small in everyday life, can look like a crisis in cosmology. So on the method map, Family 1 gets a bright label, hidden knob, calibration and astrophysical systematics. Now apply the refrain. Which family? Distance ladder? Which knob? Calibration? Is it independent? That depends. Many ladder results share rungs, anchors, photometry pipelines, and supernova standardization choices. Shared rungs mean shared risk. Now, here's the next cliff turn. If the ladder's knob is calibration, then what's the other knob that could move 9%? That takes us to the families that don't climb the ladder at all. Family 2. Local one-step measurements that assume ΛCDM. This category exists because many methods try to measure H0 without a long calibration chain. They want one step. Observe something. Infer H0. But here's the catch. A method can be local in the sense that it uses low redshift data and still be model-dependent because it assumes the standard expansion history, ΛCDM, when converting observations into H0. ΛCDM isn't just a label. It fixes the shape of the universe's expansion as a function of redshift. It tells you how to translate distances at different redshifts into a present-day H0. In their January 2026 synthesis, Pantos and Perivolaropoulos split one-step measurements into subfamilies, and they point out something striking. The one-step subset that assumes ΛCDM tends to land at the lowest H0 values among the non-ladder families. So Family 2 gets this label: hidden knob, expansion history priors. And the refrain: which family? Which knob? Is it independent? Family 2. Expansion history knob. An independence question. Even if the data are late time, how much does the answer inherit the same background assumptions that also shape CMB-based inferences? Now, Here's another turn. What if we try to do one-step measurements without baking in the expansion history? That's Family 3. Family 3. Pure, local, one-step measurements. This is the family trying to be the cleanest referee in spirit. These methods aim to measure H0 without climbing a ladder and without assuming the detailed shape of H of Z, the expansion history as a function of redshift. They still have modeling, everything does, but they try to minimize cosmological priors, so the result doesn't quietly inherit ΛCDM. In the January 2026 synthesis by Pantos and Perivolaropoulos, and this category lands closer to the middle, higher than the ΛCDM, assuming one-step group, but not rushing up to 73. So Family 3 gets this label. Hidden knob, method modeling, minimized cosmological assumptions. And again, which family? Which knob? Is it independent? Family 3. Modeling knob. Independence question. Does it really avoid both ladder calibration and early universe ruler assumptions? Or does it share hidden dependencies through catalogs, selection, or population modeling? Now the last family is the one that sounds familiar, but we're going to handle it carefully. Because this is where most people say, aha, Planck measured 67. And that sentence is exactly why people talk past each other. Shh. On Family 4, CMB Sound Horizon Free Measurements. The famous 67 value most people quote comes from the Planck satellite's measurement of the cosmic microwave background, interpreted through base ΛCDM. According to the Planck collaboration's final cosmological parameter analysis, based on their 2018 dataset release, the inferred Hubble constant under base ΛCDM is about 67.4 kilometers per second per megaparsec. But Planck didn't measure H0 the way a local telescope measures it. Planck measured a pattern, tiny temperature and polarization ripples in the oldest light we can see, and inferred cosmological parameters by fitting those patterns to a model. And the hinge in that inference is a cosmic ruler, the sound horizon. In the early universe, matter and radiation formed a hot plasma where pressure waves could travel. Then when atoms formed and light decoupled, those waves froze, leaving a characteristic scale imprinted in the sky, and later in the clustering of galaxies. That scale becomes a ruler. If you know the ruler's physical size and you measure its apparent size in the CMB, you can infer distances and expansion parameters. So what does sound horizon free CMB mean? It means you still use CMB information, but you refuse to lock in the usual absolute ruler calibration. You marginalize the ruler scale out, or use combinations of CMB-derived constraints that don't force a single sound horizon value the same way. In their January 2026 synthesis, Pantos and Perivolaropoulos found that this sound horizon-free CMB category still clusters in the high 60s, closer to 67 than to 73. So Family 4 gets this label, hidden knob, which early universe constraints dominate without a fixed ruler. Now, take a breath. We've built the families. We've labeled the knobs. Now we do the thing that turns this into a hub people return to. We put it on a scoreboard. Using the categorized averages reported by Pantos and Perivolaropoulos in their January 2026 synthesis, here's how the families line up. And I'm going to say the uncertainties out loud once, because the point isn't just where these land, it's how tightly they cluster in that analysis. Distance ladder, 72.74 plus or minus 0.40. Local one-step, assuming ΛCDM, 67.18 plus or minus 0.90. Pure, local, one-step, 70.38 plus or minus 1.00. cmb sound horizon free, 68.71 plus or minus 0.63. And if you lump the one-step family together in their analysis, the combined one-step average is 68.67 plus or minus 0.46. Those uncertainties are small enough that if this were one method arguing with itself, the fight would already be over. That's the split. Not two teams, two clusters with internal structure. Now here's the chapter flip that matters. Once you see this scoreboard, the tension stops being a mystery and becomes a question of mechanics. Which knob can move 9% without leaving fingerprints? And that's where the entire fight collapses into two giant dials. Dial 1, the distance dial. If your calibration makes objects appear slightly closer than they really are, then for a given redshift, you infer a faster expansion rate, and H0 rises. If your calibration makes objects appear slightly farther, H0 falls. That's the ladder's sensitivity. Dial 2, the ruler dial. And if the early universe ruler, especially the sound horizon, is smaller than you think, then the same observed patterns correspond to different absolute distances. And within global fits, H0 tends to rise. If the ruler is larger, H0 tends to fall. That's the inference sensitivity. So the Hubble tension can hide in two places. Either the distance scale is biased high, pushing H0 upward, or the ruler scale, or the model linking early universe to today, is incomplete, pushing inferred H0 downward. Or, and this is a serious third possibility, our uncertainty accounting is too optimistic. Hidden correlations and shared modeling choices make results look more independent than they really are. This is why the 2026 synthesis is useful as a narrative spark. Not because a synthesis is the final judge. A compilation depends on how methods are categorized, say, and on how correlations are handled. But as a map, it's powerful. It tells you exactly what kind of disagreement you're looking at. And now your refrain should feel automatic. Which family? Which knob? Is it independent? Now there's one last piece viewers always want. Okay, who are the referees? Not in production terms, in logic terms. What measurements share the fewest assumptions with both sides? In modern cosmology, there are three referee pathways everyone watches. Late time structure constraints that can be made ruler-free, strong gravitational lens time delays, and gravitational wave standard sirens. We'll tag them quickly. Late time structure without fixing the ruler, promising, and some analyses still land near the high 60s, even without a fixed sound horizon. The strong lens time delays, powerful, but sensitive to lens mass modeling and line-of-sight structure. Standard sirens, conceptually the cleanest, distance from gravity itself, but still building sample size and tightening uncertainties. And now we zoom out. You don't need to memorize every survey name or every acronym. You need the filter. So one last time, because this is the point of the whole episode. Which family? Which knob? Is it independent? Which family produced the headline number? Which knob is doing the real work underneath it? And is it truly independent? Or is it a cousin in the same family wearing a different outfit? Once you apply that checklist, the tension becomes less mystical. The Planck-based 67 is not a direct speedometer reading. It's an inference under a framework linking early universe physics to today. And the SH0ES style 73 is not assumption-free truth. It's a calibrated chain of astrophysical steps. And the fact that Webb-era crosschecks land near 70 doesn't erase the tension. It makes it more interesting. because it suggests part of the story may live inside the distance scale itself, while independent referee methods continue to mature. So the Hubble tension is not about a number, it's about completeness. If the universe truly prefers 73, then our standard model is missing something. Something about the early universe, the dark sector, or the link between them. If it truly prefers 67, then our local distance scale has a subtle bias hiding in plain sight. And if it prefers something closer to 70, then the lesson is just as profound. In precision cosmology, precise does not automatically mean independent. Either way, and this is what science looks like at the edge. The universe isn't just demanding a better measurement, it's demanding a better map of what our measurements assume. So the next time you see 73 versus 67, don't ask who's wrong. Ask which family, which knob. Is it independent? And then watch where the referees land.